All right, welcome. This is example 4 from 1 a day 2 in Math 345, section 1.2. All right, in this example, we're going to use a quadratic formula to solve a quadratic equation. Here, f of x is equal to x squared plus 62.1 x plus 1. We're setting that equal to 0, so we can use the quadratic formula. If we use the quadratic formula, we're going to find an issue with our 4-digit arithmetic using rounding. And so to get a better approximation in terms of reducing the relative error, we're going to utilize rationalizing the numerator to help reduce that error. Okay, so let's look at the process. So this is using the quadratic formula. So negative 62.1, that's the b term, right? So opposite of b, plus, because I have looking at x1, square root of 62.10 squared, minus 4 times a times c, all over 2 times a. Remember, I'm using 4-digit arithmetic. So I have 4 digits, 4 significant figures, if you will. Simplifying this a little bit more, we get negative, just pulling this down. We square this, we multiply this out and take the difference. So it's just 4 less. And then by keeping the 4 digits of accuracy, we have 3852. Taking the square root of that, and then that gives us 62.06, keeping 4 digits there. And so here is where the challenge comes in. We have negative 62.10, that's our b term. Well, it's opposite of b, plus 62.06. So here's the issue. Do you see how close these two numbers are? But we're taking, really, this is a difference of two numbers, right, that are very close together. And as we discussed earlier in the lecture, whenever you have a difference of two numbers that are very close together, that creates a challenge because we're losing significant figures. In fact, in the previous slide, we were looking at how that happens. And so you can see here, we're losing these two, and we're going to be doing something with this one here almost immediately. Okay. All right. This difference being close, we cancel out the number of significant digits that were allowed, and that's what introduces this relatively large error. So if we look at the floating point value, we get the solution is negative 0.0200, and then the relative error for the exact value of x1 being negative 0.01610.723. So we get a relative error of 2.4 times 10 to the negative 1, or about 25%. This is about 24%. So that's a relatively large error. That's a relatively large relative error. So what can we do to reduce that relative error? Well, that's where the computing the rationalizing the numerator can come in. Let's take a look real quick at the floating point values for the second root. And so here, that solution is negative. This is for the second point, the floating point operation. Same rounding to 4 digits, negative 62.10 minus 62.06. But see here, we're adding two negatives, so it's not the difference like it was in the first root case. And so you get a negative 124.2 over 2, which reduces to negative 62.10. The actual value of the second root is negative 62.08390. So you can see that they're really close together. And actually, that relative error gives us something on the order of the 10,000ths, right? So, or as a percent, this would be, if you move this over, it'd be 0.0. Well, let's just write it out so you can see the whole thing. 0, 3, 4. So 1, 2, 3, 4. And so the percentage of this would be, if we move it over twice, would be 0.0340%. I need to add another 0 there. So this would be the percent. So the relative error here is significantly smaller than the 24% relative error in the x1 root. Okay. All right. So let's look at what do we need to do then to simplify this, or to reduce that relative error. Okay, and so to obtain a more accurate four-digit rounding for x, let's rationalize the numerator. So that's the punchline here. And so if we did that, if we rationalize the numerator, we're going to multiply. So since our x1 was, in this case, we're adding here. So to rationalize the numerator, you take negative b minus this radical and multiply top and bottom by that. You're going to get a difference of squares on top, which is what is really nice about it, and everything cancels out. And then downstairs, you're going to get negative 2c over b plus the square root of b squared minus 4ac. And so we're going to plug in our values from our f of x here, which were, just as a reminder, we're 1, 62.10, and 1 again. But again, we're using four-digit arithmetic, so we need to have four significant digits. So we have negative 2.000, 62.10, and we're going to add here the same result, 62.106. So here now, we're adding the result. That's the same computation, just carrying over the numbers from last time. And so instead of a difference now, we have a summation downstairs. And so we have negative 2 divided by 124.2. And then this gives us a result or a value of negative 0.01610. And now if we compare that to our actual value for x1, you get negative 0.01610,723. And so you can see that they're almost identical, at least out to the fourth digit. Okay. So the relative error, and that's reflected in the relative error. The relative error is 6.2 times 10 to the minus fourth. So that's going to be on the same order as the floating point relative error on the second root, or as we saw here. So by rationalizing the numerator, we went from 24% error down to 6.2 times 10 to the minus fourth error, right? So that's a huge difference. That's 3 orders of magnitude difference in the amount of error introduced by not rationalizing the denominator. Okay, so that's significantly more accurate. All right, so it's also interesting to note that if you thought, well, maybe if it works so well on the first one, let's try it on the second one, right? So x2 is negative 2c divided by b minus the square root of b squared minus 4ac. So rationalizing that x2 denominator, we would get this. Now, this would be a good idea to use if our b term had been negative, right? So if b is less than 0, this is the form that you should use to reduce that error. But let's see what happens if we don't, right? So this is just my talking about it over here. So if we plug in our values here, we get negative 2 divided by 62.10 minus 62.06. So here's the challenge, and this is what I'm talking about over here. So just like in the first example, these two numbers are really close together. So you're going to get a difference that's super close. So that's one error that gets introduced a lot, or introduces a lot of error. That's one arithmetic or one operation that introduces a lot of error. But this one's compounded because now you're also dividing by that number, which is really small, and you're dividing that number that has a lot of error in it. And since the number is small and it has a lot of error, it's going to introduce a significant amount of error. In fact, you can see that here in our solution, right? It says that our value for x2 in the floating point representation is negative 50. But we know that the actual root is negative 62.038, 8390. So clearly, just in the value, right? It's at least 12 units away. So that's significant error. And if we thought about computing the relative error, you could see that that would be very large indeed. Okay. All right. So what have we learned from this experience? Why did we go through this example? Okay. So finally, it's okay to add numbers that are close together, right? That doesn't introduce a lot of error. But when we subtract two numbers that are really close together, as we talked about earlier in the lecture, that is really bad. It introduces a significant amount of error. And then if we're dividing by a number that's really small, that's what this notation here means. We're dividing by a number that's really small and it has a lot of error in it. You're going to see, just like we saw here, right? It's going to introduce a ton of error. And so it really can drastically affect your results. And sometimes it's so subtle you don't even notice it. But here we have the compounding of two errors. And so that kind of brings in a second point. The first error is bad enough, but if we include then the second error, right, or the second operation, the more operations that we're introducing, especially if those operations contain errors in them, then it quickly blows up the error. The error propagates through it significantly, and it continuously reduces the number of significant figures that are actually significant figures, not just noise, if you will. So we did recognize that rationalizing can be helpful. That's one of the tricks that we can do. However, we have to even just doing that isn't going to guarantee that we get a reduction in the relative error, as we saw in our comparison of x1 and x2 roots. We have to be careful about how we're paying it, or um, how the numbers are relative to each other, and then also the error that's introduced by the operations. And then again, reducing the number of calculations is huge. We saw that in the example with the second root, the number of operations can greatly exaggerate the amount of error introduced by a single operation. Okay. All right, so let's use these ideas then to look at this last example, or the last part of the example. We saw that f of x is equal to x cubed minus 6.1x squared plus 3.2x plus 1.5. And we want to evaluate at the point x equals 4.71 using three-digit arithmetic. So we're going to compare here both for rounding and for chopping. I think the comparison is very helpful to kind of illuminate some of the differences that occur and how errors can propagate. So we will use a nested method to do this. And you may be wondering, where did that come from? Well, playing around with the number of operations with this, you think about how many operations are here, right? We're going to multiply x 3 times, and then we're going to multiply x 2 times, and then we're going to multiply x once here. Okay, and then we have another multiplication, and then here, and then we have a difference, a sum, and another sum. So we're creating a bunch of different exercise or different evaluations. And if we do this nested thing, where if you kind of think about it as kind of like factor by grouping in a sense, right? So you start out here and you pull out, well, both of these terms have a GCF of x squared. So I'm going to pull that out. Okay, and then if I look kind of like at this part, well, that looks like they have an x in common, right? So I'm going to pull out that x. And so I get this thing, and then there's no more common factors to pull out. And so look what that does. I have a difference, and then I have a product, and then a sum, and then a product, and then a sum. So I have 5 operations here, whereas here I have 1, 2, 3 multiplications, 4, 5 multiplications, 6 multiplications, 7 multiplications. So I'm already at 7 multiplications, a difference, a sum, and a sum. So I'm quite literally doubling the amount of calculations evaluating it directly here. And again, so that propagation of error can spread quickly through. And we're going to introduce error each time because we're using three-digit arithmetic. So, all right, so if we compare those and plug in the information, we can see here, plugging in f of 4.71, we plug in 4.71 everywhere, we see an x, and compute that. Using three-digit chop, we got negative 14.2. And if we use three-digit rounding, we get 14.3. So you can see that they're close relative to each other. They're off in the tens place, which for these kind of examples is pretty common. Okay, now if we compare that to the relative errors, sorry, should mention that here. So the relative error, the relative error here for the three-digit chop is 0.0045. And the three-digit rounding, we got an error, a relative error of 0.0025. So notice that this is kind of like almost half of that, right? So then we come back here and we look at three-digit chopping. So this is evaluating 4.71 directly into the RF of x here. So just plugging in for x cubed, we get 4.71 cubed, 4.71 squared, 4.71 times 3.2. Yeah, so if we do that and look at the relative error with respect to the actual value and we get an error of 0.05 and 0.06. So this is a 5% error and a 6% error. So that's pretty large. relatively speaking, especially when you compare it to just doing the simple nesting. Uh, these are an order of magnitude off. In other words, this is 0.05. So if I kind of rounded this up and call that 0.005, that's 10 times larger. That's a significant difference. It's a whole order of magnitude. And this is, likewise is not only is it an order of magnitude, it's also a multiple of that. So this is 0.06, this would be like 0.03, right? 0.003. This is like an order of magnitude times two or 20 times bigger, right? That's significantly bigger error. And all we did was reduce the number of calculations by using this nesting method. Okay, so I hope that this kind of helps illustrate the value and how errors can change or propagate through, and gives you some strategies on how to reduce the number of errors that show up in your calculations. All right, I hope that was helpful, and I'll see you in the next video.